Hey, CS170. Today we're going to be covering the next subtopic of divide and conquer, namely the fast Fourier transform. So if you want to follow along in the textbook, section 2.6 has a great overview of how FFT works and also a bunch of details about the math. But today I'll be kind of going over the motivation and some of the high level how FFT kind of works. So the motivation behind studying FFT is that we want a fast algorithm to multiply polynomials. So for example, here, if you see, we have polynomials A and B, both are degree D polynomials. And we want to find what the product of A of X times B of X is. So I just call that product C of X here. And so essentially, we want a fast algorithm to find this product. And so as you may have known from CS170, if we take the product of two degree D polynomials, we're going to get a degree 2D polynomial, which is what I've said, which is what I've expressed in this line here. And so let's kind of take a look. Let's go coefficient by coefficient. I'm going to take C sub D. Let's look at the coefficient in front of the x to the power of D term. And so essentially, to find the entire C of X polynomial, we're going to have to calculate each of these coefficients. So let's kind of deep dive and look at how the calculation for one of the coefficients work. So for example, for the C sub D term, right? Since the power of the X here is D, we're gonna have to pair different variables, different expressions in A of X and B of X and see what gives us the product so that the X term is to the power of D, right? So for example, if we look at A sub D times X to the power of D, and we multiply it by B sub 0, we're gonna get A sub D times B sub 0 times X to the D. And so since there's an X to the power of D term, we know that it's gonna contribute to the C sub D value. And so the next term we'll get is A sub D minus 1 times B sub 1 times X to the power of D. And then we can kind of keep going. B sub 2 times X to the power of D, all the way until we get A sub 0 times B sub D times X to the power of D. And so again, all I'm kind of doing here is taking different combinations, different matchings of different terms in A of X and B of X, because we're trying to find the coefficient C sub D, which is a coefficient of the X to the power of D term in the product. And so if you look at this entire calculation, there's going to be D terms here, right? Or actually D plus 1. But again, we're just, for this, I'm just kind of trying to show what the runtime of this preliminary algorithm is. So it's going to be, the number of terms is kind of O of D, right? So for each coefficient, we're going to have to find out basically around D products, we're going to have to find out A sub D times B sub 0, A sub D minus 1 times B sub 1, et cetera, et cetera. And how many coefficients are there here? There's about 2D plus 1, right, coefficients. Because there's 2D plus 1 terms, which means we have to find out 2D plus 1 coefficients. And so for each of these 2D plus 1 coefficients, we're going to have to do on the order of D calculations. So if we kind of multiply those, we're going to get an algorithm that runs in O of D squared runtime. And so basically, what is this showing? It's basically showing that if we kind of go the quote unquote basic way, which is kind of multiplying these polynomials by hand, matching different coefficients in A of X and B of X, we're going to get a pretty, a quadratic runtime algorithm, right? And so that's pretty good, but we can definitely do faster, right? And so that's kind of where FFT comes in. We're using FFT to speed up the polynomial multiplication process. And so to kind of give an overview of the design or where FFT comes in, we're going to have to understand the two different ways we can express polynomials. So one way is in this way, which is called in the coefficient view. So if I just copy this over real quick. So this is what we call kind of the coefficient view of things. There's also another way we can express polynomials, and it's in the values. So if we plug in a bunch of values into a of x, for example, like a of 1, a of 5, et cetera, we'll get some values out of it. Let's call this p of 1, let's call this p of 5, et cetera, right? And if you remember from CS170, if you have if you have a degree d polynomial, right, and you don't know what the polynomial is, but you do know some of the values and outputs of those values, you can use what we call as interpolation to recover what the actual polynomial is. So if you have a polynomial, in this case, it's degree d. If you have d plus 1 inputs and outputs into that polynomial, we can recover the polynomial. We can get back what the original polynomial is. And so that's a different way we can express polynomials, right? So one way is the coefficient way. And the other way is in terms of values. So the coefficients way is, so this is kind of what the coefficient way looks like. And this is what the values looks like. So in terms of the values, we're gonna get pairs, right? So for example, if we evaluate A at 1, we're gonna get P1. So our value pair would be 1, comma, P1. And this would be 5, comma, P5, where P1 and P5 are whatever we get when we input 1 and 5 into the polynomial A. And so let's try to use this values view of the polynomial to come up with a faster algorithm, right? So what can we do? If we have A and B in these two polynomials in the coefficient expression, right? The coefficient view. So this is what we're given, right? These two polynomials. So now one idea that we can have is, and as it's kind of explained in much more detail in the textbook, but just an overview, we can kind of evaluate, we know that C, the product of these two, has degree 2D, which means if we have 2D plus 1 points of C, then we can recover what the actual polynomial C is. And so how can we get 2D plus 1 values of C when we don't even know what C is, right? But the cool thing here is that since we know A of X and we know B of X, we can evaluate, let's take in the random value of 1, right? We can evaluate A at 1, multiply it with B's evaluation at 1, and that's going to give us C's evaluation at 1, right? So even though we have no idea how C looks, we can plug in 1 into A and into B, multiply those two, and get what C is at value 1, right? And so using kind of this approach and knowing that we need 2D plus 1 values to recover it, how C actually looks, one idea that we can have is evaluate A and B, evaluate at 2D plus 1 different points. Or let me say values. So essentially what that's going to give us is it's going to give us 2D plus 1 points of C, right? And so then we can go back using these 2D plus 1 points or evaluations. We can go back from this values view to the coefficient view. And so we use interpolation, right? So again, just to give a really high level overview of how this works. We have A and B in coefficient expression, the coefficient view. We then evaluate A and B at 2D plus 1 different points, right? So we evaluate them, we get them here, we're at this values, we have 2D plus 1 different values. We use those 2D plus 1 values, we use interpolation, what we learned in CS170, to go back and recover the coefficients of C. And so at the end of this, we're gonna get back what C looks like and what the coefficients of C are. And so where FFT kind of like comes into picture is in this evaluation step. Why? Because normally, if we just want to evaluate A and B at a bunch of different points, let's say 2D plus 1 points, that's kind of like the straightforward way of doing it. But it turns out that doesn't really help us come up with a faster algorithm. It keeps the runtime the same, right? Where FFT comes in is it gives us a much better way of actually evaluating the polynomials A and B at 2D plus 1 different points. So yeah, that's just kind of like giving you a bigger picture of like where FFT fits in. And as you'll like understand later, FFT also helps out with the interpolation step. So that's where the inverse FFT comes into play. Again, this is just to give like a high level overview of like where FFT comes in, so you guys have a sense of where, like how things are working. And in the next video, we'll get into the details. Okay, so diving into the details of FFT, we want to speed up the evaluation process. So to do so, we're going to have to find ways that we can make that whole procedure more efficient. And so the first step that we take is, let's go over the first step, right? So take a look at A of x, it's just some random polynomial. So the first step that takes place in kind of like building the intuition for FFT is splitting the polynomial into two smaller expressions, sub-expressions, basically. The first one is on the left side here. It's basically the sum of all of the even powers in all the terms that have even powers, right? So if you look here, it's 4 times implicit x to the power of 0 plus 3x squared, which is even term, plus 5x to the 4th, which again is an even term. And the second expression is here. It's the sum of the terms that are odd powers, right? So 6x to the power of 1 plus 2x to the cubed. And so to go one step further, let's factor out an x right here. So then what we do is we kind of denote this expression as a sub e, which is kind of like the even terms of a of x, and this expression as a of o. So 6 plus 2x squared would be a of o. It's kind of like the odd terms, right? And so basically now we can express a of x as a of e of x squared, since each of the terms here are x squared, right? They're all even, which means they're all x squared to the power of something. Plus x times a of o times x squared as well. Because that's kind of like the motivation why like I factor out an x right here, is because now all of the terms remaining in a sub o are, they kind of look like exactly like this even expression, right? There's 6 times x to the power of 0 plus 2 times x squared, et cetera, et cetera. And so now we can express this polynomial a of x as a of e of x squared plus x times a sub o of x squared as well. And so, okay, what's the motivation behind doing that? The motivation behind doing that is we want to make this whole process efficient. So we want to find, again, we want to evaluate polynomial a and polynomial b at 2D plus 1 points and then take the product of those. So we want to find kind of the points that make it as easy for us as possible to do that. And so if you take a look at, so this expression here is kind of when we plug in x. If we plug in negative x into the same thing, you'll notice something really cool. It's that, so if you plug in negative x into where x is, all the places where x is here, you'll get that negative x squared just stays as x squared. And then here there's a plus x that turns into a minus x. And then you have a sub o of negative x whole squared stays as x squared. So now what do you notice here? What you see here is that when we plug in the points x and negative x into the same polynomial a, we get that a lot of actually the bulk of like the two values are pretty much the same, right? In both the a of x and a of negative x case, we have this term, a sub e of x squared, that's pretty much the same, and a sub o of x squared, also the same. The only thing that changes is this sign. So pretty much, again, we're trying to make this process efficient. We're trying to, so here, we see that there's a lot of repeated work, which means we only need to calculate a of e of x squared once and a of o of x squared once. And doing that once kind of sets us up to find out 2 points, like a evaluated at 2 points. So it basically like halves the work that we need to do. So I'm just gonna like summarize that here. The repeated form halves the work. Since we want, like, let's say we want to evaluate a at, let's say like n points, right? Now, if we plug in x and negative x, we have so much repeated work that it kind of sets us up to only do n over 2 of the work, right? And so that's kind of where the divide and conquer concepts come into play. We have this a of x polynomial that we want to evaluate at a bunch of points. We split it up into a sub e of x and a sub o of x. And so kind of we kind of branch off into two much smaller problems, right? Because as you see here, each of these like a sub e and a sub o are now kind of like half the size of a of x. And so again, that kind of goes back to the divide and conquer principles. And so all we need to do is come up with kind of choose like a bunch of plus minus pairs, right? Because we evaluated at x and minus x at a bunch of different values. So let's take like, for example, random numbers 3 and negative 3, we evaluate, and we evaluate at like 5 and negative 5, and we keep doing it for however many points that we need. And it kind of depends on the degree of a, right? And so again, here you can see we want to evaluate a sub e of x squared and a sub o of x squared, right? And so it kind of breaks us down. So we're originally at the a sub x level, and then when we go down into the a sub e level and the a sub o level, we kind of combine these, and we want to look at the squared value, right? 3 squared and 5 squared, because that's what we're putting into a sub e and a sub o, the squared values, right? So we have x squared. We're going to want to evaluate a sub e of x and a sub o of x at these points. And again, there's going to be a bunch of other points, however many you need. So, okay, it seems like all straightforward so far. But there is one problem though. We want to divide and conquer all the way to the base layer, right? We can't just do one layer, like kind of go from a sub a of x to just kind of split it up once. That's not how divide and conquer works, right? We want to divide and conquer until we hit the base, like smallest building block problem, right? And so to do so, we're going to have these values, like this 3 squared, 5 squared. We're going to get a bunch of other squares, let's say like 7 squared, 10 squared, etc. We're going to have to be able to combine these in the same way, right? So there's going to have to be like another value that we can combine with 3 squared that will serve as its plus minus pair, right? The whole reason why it was so easy for us to divide it at the first step was we were able to find this plus minus pair, this x and negative x, that simplifies the work for us a lot, right? So the difficulty here is in the first layer, we kind of choose those plus minus pairs. We choose a 3 and negative 3. But once we divide it, once we go one layer deeper, we kind of lose that plus minus pair, right? We don't know if there's going to be another value here that we can use as a plus minus pair. In fact, 3 squared is 9. We're going to have another value be negative 9 in order for us to use this pair as a plus minus pair to kind of make this process efficient. But the problem is, so yeah, we're going to need, so again, kind of starting over here, we're going to need, so we already have 3 squared, which came from the 3 and minus 3, but we're going to have another pair that yields us negative 3 squared. But that, you should immediately stop there and wonder, like kind of imagine like how in the world would we ever combine 2 values to get negative 3 squared, right? So originally, if we plug in 3 here, we'll get a sub e of 3 squared here. And if we plug in negative 3 here, we'll still get a sub e of 3 squared. So that's kind of where like a lot of work is, it's made like a lot more efficient because there's a lot of repeated work. But the whole problem here is that we can only do that at 1 layer. We can't repeat for future layers because we're going to need 2 values. We're going to have to choose 2 values that gives us the pair of negative 3 squared. And so that's where kind of like it should ring a bell, like complex numbers might be the way to go, because using complex numbers, we can take the square root of like a negative value, right? We can deal with these negative square values. And that's what the next video Lily's going to cover.
Thanks, Neil. In this video, we'll cover why it's a good idea to use complex numbers, and in particular to the nth roots of unity as the points of evaluation. So there's huge construction outside my apartment, so please ignore the drilling noises. But first, let's give a quick recap of complex numbers in polar form. If you're already familiar with this, feel free to skip ahead for a couple of minutes, and I'll see you then. But for everyone else, every complex number can be written as a plus bi, where a and b are real numbers. We can draw this on the complex plane as the point a comma b, where a is in the direction of the real axis and b is in the direction of the imaginary axis. Equivalently, we can write this in polar form, r e to the I theta. So r describes the magnitude, or the distance to the origin. So this is r. And theta describes the angle that this connecting line makes with the positive real axis. This is theta. So again, given the information r and theta, we can specify a point on the complex plane, and we can specify a complex number this way. These are sort of equivalent ways of representing complex numbers. And in this particular mini lecture, we're really interested in polar coordinates because it gives us a nice way to visualize multiplication. So if we have 2 complex numbers, r e to the I theta and then r prime e to the I theta prime, multiplication yields r prime e to the I theta plus theta prime. So we are summing up the angles but multiplying the magnitudes. You can imagine that if we're dealing with the unit circle on the complex plane, or numbers where r equals 1, then e to the I theta times e to the I theta prime is just e to the I theta plus theta prime. So on the unit circle, a multiplication is just summing angles. All right. From this point of view, if we're multiplying numbers on the unit circle, we have a very nice way of thinking about it visually. Now let's talk about roots of unity. So the sort of definition is that if I have, say, I call omega to the n equals 1, all the solutions, I call them nth root of unity. Okay, so clearly, anytime 1 is always a solution to this thing because 1 to the n is always 1. But in general, there are a total of n solutions that satisfy this equation. And on the complex plane, they look like endpoints spread evenly on the unit circle. I don't know how many points I drew here, maybe 1, 2, 3, 4, 5, 6, 7. So this would be a representation of the 7th root of unity, sort of loosely speaking. I'm sort of, just spread evenly. This is not as even as I thought it would be, but trust me, they're spread evenly. As an exercise, you can go home and try to convince yourself why this is, that the nth roots of unity are, well, endpoints spread evenly on the unit circle. All right. In particular, we're interested in the 2 to the nth root of unity. What this means is I take, well, 2 to the n points on the unit circle. So in the case that n is equal to 3, we get 8 points here. 8 points. All right. And I have some very nice properties that 2 to the nth roots of unity satisfy. So the first property is that they're plus minus paired. This means that if omega is a nth root of unity, so if omega to the n is 1, then that implies, omega to 2 to the n. Let me erase this and write this again. Omega to the 2 to the n is equal to 1, then I can say that negative omega to the 2 to the n is also equal to 1. And this is because 2 to the n is always even, and so this is equal to omega to the 2 to the n. The other nice property is that it behaves well under squaring. So what I mean by this is that if I have omega as a 2 to the nth root of unity, then omega squared is a 2 to the n minus 1 root of unity. Why is this? We can see this by sort of rewriting this equation. We can write omega to the 2 times 2 to the n minus 1, which is just sort of taking out a 2 from this expression here. And we can sort of rearrange this to say this is omega squared to the 2 to the n minus 1 power. Okay? And this is equal to 1. So what this means is that omega squared as a number to the n minus 1 power is 1. So omega squared is in fact a 2 to the n minus 1 root of unity. What is this good for? We can notice that if omega squared is a 2 to the n minus 1 root of unity, then it means negative omega squared is also a 2 to the n minus 1 root of unity. So even once we square them, it's still plus minus paired. So these are very desirable properties because you might remember from what Neil said, we had this problem. Let's recall what this problem was. We wanted to find a set of numbers to evaluate a to the x. We want to find some set of points such that we can plus minus pair them. In his example, we say we're evaluating the even terms and the odd terms. And just as a reminder, a of x is equal to ae of x squared plus x times ao of x squared. So we want to evaluate these points in x squared. And we came up with a sort of clever scheme by pairing up points so that we don't have to evaluate at so many points. We can evaluate sort of half the points. So in Neil's example, we had -3, 3, -5, and 5. Right? So then when we're evaluating a of x, on the next level, we only have to evaluate at, say, 9 and 25. But we had a problem. Our problem was that once we do this first level, we cannot find plus negative pairs on this sort of plus minus pairs on this level anymore. So we can't keep combining further, right? So that's problematic. But the 2 to the nth roots of unity give us a very powerful tool to make this work. Let's see how this is. So again, at the top level, we're interested in evaluating a to the x, and the next level, we're interested in evaluating ae of x squared and ao of x squared. At the top level, we have omega 1 and negative omega 1, omega 2, negative omega 2, and sort of goes on and on, right? And all of these numbers are 2 to the nth root of unity. I don't know, R, O, I'm pretty sure this is not a thing, but let's write this since I'm running out of space. So these are some points spread evenly on the unit circle, and if you take them to the nth power, they become 1. All right, and they're plus minus paired, as we said before. Each number has its pair. All right, so now on this next level, we combine these to have omega 1 squared, omega 2 squared, etc. And so now on this level, we're dealing with to the n minus 1 roots of unity. And on the unit circle, this would look something like this. Right? If we previously had 8 points, 1, 2, 3, 4, 5, 6, 7, 8, then now we have only 4 points because we pair them up by pairs. And again, we have plus minus pairs. So this allows us to keep going with this. And at each level, we're guaranteed to have plus minus pairs. Because at each level, we're still dealing with 2 to the something roots of unity. And so maybe you're wondering what this level, what we're evaluating at this level. Well, we're just evaluating, say, the even terms of AE and the odd terms of AE, and then the even and odd terms here, right? So this gives us a very nice divide and conquer algorithm, right? So let's write down the recursion. We're interested in the running time of FFT, so t to the n. N is how many points we're evaluating at, right? All right, so at each level, we're breaking up into 2 evaluations, 2 polynomials that we're taking as subroutines. So 2 times t of something. What is this something? How many points are we evaluating at each level? Well, we're having the work at each level because we're pairing by plus minus pairs because we're able to square them and get the same value. So each problem is only half as big. And we add in a linear term. What is this linear term? This linear term comes from a to the x equal to ae of x squared plus x ao of x squared. So after we do these 2 subproblems, we need to combine each point. We need to combine the value of each point. And this is just linear time arithmetic. All right. So by the master theorem, we have that t of n is in fact O of n log n. Okay, so maybe you're not excited about this n log n yet, but let me tell you why you should be very excited at this point. So we've been sort of thinking at the abstraction level of constructing the algorithm explicitly, but now we'll go back the abstraction to the level of polynomial multiplication. So this is, the huge overview. The entire motivation of doing all of this work is to multiply polynomials efficiently. Remember, we started with the coefficient form, where we represent some polynomial by just a set of its coefficients. So we're dealing with a degree d polynomial. Okay, and then it's hard to multiply in this coefficient form, but we said it's easy to multiply in values form, right? Or points form, where we describe the same polynomial by its value at a set of points. So we have, say, x0, y0, x1, y1, all the way up to, say, xd, yd. All right. And it's easy to multiply here because, if you have 2 points, 2 polynomials, a1 and a2, and you have their value at, say, x0, then you just multiply their y values. Okay, so we want to build a bridge here. And this is our evaluation scheme. And remember, this whole process of FFT that we're talking about here is this evaluation scheme. And this is done in time n log n. All right. Now, we haven't covered this, but the inverse FFT takes values form to coefficients form, and it's called interpolation. So this is inverse FFT. But if you read the textbook, this is basically the same algorithm, just taking the inverse of the matrix we're multiplying by. I won't go into too much detail here, but this is also O of n log n. So in this entire polynomial multiplication problem, we take, say, two polynomials, ax and b of x. We do this evaluation process, which takes O of n log n time. And then once we're at the values form, we multiply the y value at each x value. And we do this for, like, say, d points. Okay, this should be d. Let's say n here instead. Let's just note that n is equal to d here. All right. And once we get to the values form, we do this for d points or n points. And this is sort of just arithmetic, which will only take O of n time, right? And then we come back through interpolation and again spend O of n log n time. Now we finish multiplying. So this entire process will take us n log n and n log n time, which is n log n. And this is awesome because previously, when we first started, all of this had to take n squared time. This is smaller than n squared time. So this is very nice. Now we can go one more abstraction level. We go all the way up again, and we use FFT as a black box. So even though we spent a ton of time on FFT as an algorithm, this is perhaps something that you'll keep using for the rest of this class. This is that if I have two polynomials, a of x and b of x, with max degree n, then multiplying them only takes O of n log n time. So yeah, this is using FFT as a black box. You pass in two polynomials, and you get their product. All right. And so now that we're at this very top level of abstraction, we're done for the day. And yep, thank you for coming. And then in the next section, we will go over an overview of all the discussion problems for this week.
Hey, what's up guys? Avi here and welcome back to week 2 of the mini lecture. In this video, I want to go ahead and take what Neil said and kind of give you the high-level intuition behind the matrix multiplication that actually happens in FFT. Let's dive right in. So first thing first, we saw from Neil's point of view the high-level intuition of FFT in the simple polynomial representation. So we saw that if we had a polynomial a of x and we wanted to evaluate this polynomial, what were we supposed to do? We divided that into its even and odd powers, and we saw that we can evaluate the polynomial a of x at n points, but rather than doing so, we can apply a divide and conquer approach and evaluate this polynomial at its even and odd powers at just n over 2 points. And that was the whole reason of using divide and conquer and made this algorithm very efficient and gave it an O of n log n runtime. Now the question is, okay, that makes sense, but FFT in general uses this matrix multiplication. So what's happening there and what's the high-level intuition behind that? That is the point of this video. So first thing first, just to give some clarity, we can rewrite that same type of evaluation with our matrix over here, our FFT matrix, times our vector of coefficients. So the vector of coefficients would be a1, a2 through an, and we would essentially be evaluating this matrix multiplication right over here. So the definitive FFT algorithm takes an input vector a, which is the one over here, and a complex number w whose powers are from 1 to w of n minus 1, and it's essentially multiplying this n by n matrix by our vector a. And so by doing this multiplication, we essentially want to show how we can still apply divide and conquer on this matrix multiplication and still get the same results in the O of n log n time that we showed previously. So one way we can write this out is we can essentially draw a box over here. And in this high level box, I'm going to go ahead and give it a label. And I'm going to call this, I'm going to make it a square. And I'm going to call this box W to the power JK. And so here, J and K will be my rows and columns respectively. My J and my K will be the J is row, K column. And so this again is my representation of my FFT matrix times my vector over here. And so what I'm going to go ahead and do is initially write out A0, A1 up to AN-1. Made a small mistake over here. Sorry about that. This should be A0, A1 to AN-1, counting at 0. And so with this multiplication, what we're going to go ahead and do is essentially break this matrix up into its even and odd columns. So just like our original multiplication of, evaluating our polynomial a of x by breaking it up into its even and odd polynomials, we're going to do the exact same thing by getting the even and odd columns. So what we can go ahead and do is create this exact same box, and inside of this matrix, just reposition the columns such that that can happen. And so what we're going to go ahead and do is divide this in half over here and state that, okay, my columns in this section are going to be what? They're going to be 2k. Okay, so column 2k, and this is going to be column 2k plus 1. And here, my k ranges from 0 to n over 2 minus 1. Okay? So what does that imply? If I take, let's say, k equals 0, I know that my 0th column is going to be this type of subsection over here. And I know that my corresponding k, like the odd column here is what? 2 times 0 plus 1, which is 1. And so the odd column is now right over here. So I have 0 to be here, I have 1 to be here. Similarly, if I continued this intuition, I would have, okay, if I have k equals 1 now, I would have my 2 times k is 2, 2 times 1 plus 1 is 3. And so I'd have my new column over here, 3. And so on and so forth, you would get all the even columns in this type of region, and you would get all the odd columns in this region as well, okay? So we're essentially splitting up our matrix in those even and odd columns. Let me go ahead and undo all these changes so it's a little bit more cleaner. And so now that we went ahead and did that, and we have these even and odd columns, we can go ahead and write out what this new type of conjecture would look like. So what is the actual multiplication happening here in the FFT format? Well, we know that our column ID is 2k in this case. So this just became, we still have j over here. So it's w and to the power of 2jk. And then similarly for our odd columns, what does it become? Well, we have this extra plus 1, so this just becomes w to the j times w to the 2jk. So here, all we've done is we've divided our matrix into the even and odd columns, okay? And so this is our even, this is our odd, and we're multiplying this by our same vector, except with the vector, we can also divide our vector into the respective even and odd columns, so we're still getting that same multiplication result. So here, we know that our even columns are mapped to the even numbers, and so we can say a0, a2, ... all the way up to an-2. And then similarly, once we've gotten all the even values, the next step is to go ahead and map the odd values. And so we'd get a1, a3, ... to an-1. And so what we've done is we've literally just taken this structure and reformatted so we have the even multiplication first on the left-hand side, and then the odd multiplication on the right-hand side. And so that's the intuition. If you go ahead and break this down even further, you can go ahead and split up this row j into rows j, and then rows j plus n over 2. So again, just offset by half. And so I'm going to go ahead and draw the final type of diagram to explain the intuition here. And so this becomes over here, again, my box. Let me go ahead and draw this out. We have our even and odd columns that we just discussed. And so we have 2k for our column over here, 2k plus 1 for a column over here. And then let's go ahead and divide this in half as well. And we're creating these 4 components where each one corresponds to a row. And so here we're saying that this will be row j, and then this will be row j plus n over 2. And the reason why we're saying this, like nothing is changing here, right? Like j and j plus n over 2 was the exact same thinking, except the j and j plus n over 2 helps us create these 4 compartments that we can go ahead and calculate what the actual evaluation would be. So here j represents the values from 0 to the same thing as k, 0 to n over 2 minus 1. And imagine this is just an offset, right? So we're just like dividing our section into 4 compartments. And so here what we can go ahead and say is this evaluation becomes w to jk, this one becomes w to jk, right? Nothing changes, the exact same thing. But now what we can go ahead and do is we can apply the wn over 2 to be equal to -1 and w to the n to be equal to 1. And so we can simplify the entries in the bottom half of the matrix by mentioning here that w to n over 2 is equal to -1 and w to the n is equal to 1. And so here we can go ahead and say w to the j times w to jk. And then at the very bottom over here, we would go ahead and say negative w to the j times w to the 2jk. So notice here that the top left matrix, this one, and the bottom left matrix over here are the exact same. And on the right hand side, you can see that these matrices, the top right and the bottom right, the only difference is a factor of a negative between w to the j and negative w to the j. And so the final product vector that we can write, and again, all this is in the textbook, but just for explanation, we can explain this to be our subproblem w to the n over 2 times our evens, so a0, a2 to an minus 2. That's our top left. Our bottom left becomes wn over 2 times a0, a2 to an minus 2. Our top right becomes wn over 2 times the odds, a1, a3, an minus 1. This times w to the j, right? Let me write that a bit nicer. So this times w to the j. And then last but not least, we have negative w to the j times our wn divided by 2 times a1, a3 up to an minus 1. And so this is the final intuition behind, FFT in the matrix format. And so what we've done is we've taken the product of our mn of w matrix. So we have this massive matrix, and we multiplied this by our vector a0 to an minus 1. And all we're saying is this was initially a size n problem. And what we're doing is we're expressing this in terms of two size n by 2 problems. Again, it's the product of mn divided by 2 of w squared times our evens, a0, a2 to an minus 2. This was, again, the top left and bottom left compartments of our original matrix, the top left and bottom left. And then we're also saying that the other side of this was the odds, where we have our mn over 2 times w of w squared times our odds, a1, a3 to an minus 1. And then you have like that extra factor of w to the j, which you're multiplying against this, and that gets you the final answer, whether it's positive or negative, based on its top right and bottom right subsegments. So that goes ahead and applies divide and conquer on the FFT algorithm, and this divide and conquer strategy gives you O of n log n runtime. And so now the final question becomes, okay, we've taken this matrix, we've broken it down into the left subsection, the right subsection. Now it's very clear what multiplication is going on, but now once I have my evaluations, how do I interpolate and guarantee that my evaluation will also run an O of n log n time? So in this case, how can I guarantee that my going from my actual coefficients to values and then back to the coefficients, how can I guarantee that my interpolation will also run an n log n time? And so the thinking here is that my FFT matrix, my mn of w, and the inverse of mn of w, so again, like the whole strategy of interpolating going back, both of these will have our FFT divide and conquer strategy applied. And so in both of these cases, the inverse of our mn matrix and the normal mn matrix will have the divide and conquer properties such that once you've gotten the values and you want to interpolate back to coefficients, you've gotten like the actual values from FFT and you're going back to the coefficient representation, that interpolation, you're applying the inverse of your FFT matrix, and that inverse will still hold the even and odd polynomials, and you'll still be able to apply this O of n log n algorithm, which is divide and conquer, on divide and conquer, and we'll be able to apply this on the inverse multiplication of the FFT matrix. And so by doing so, both of these routes, going from our actual coefficient representations to value representations and value representations to coefficient representations, both run an O of n log n time, giving us a final runtime of O of n log n.
1, 2, 3, come on,